Okay. All right. Welcome, everybody. Thank you for joining me here now. I'm Lamberto Basti. I work at JetBrains. I work in the package search team, the recently popped up tool window at the bottom of IntelliJ that tells you how to change your dependencies. Soon available also on Android. But anyway, Android Studio. Anyway, let's start today with the talk. And we're here to talk about Kotlin's flow. So the first question is, what's a flow? So the flow is the Kotlin take on reactive streaming. All right. So I guess most of you already had some experience with Rx, Java, or maybe Rx in some other languages. And well, Kotlin's flows is just equivalent, but using coroutines. Now, if you're already using Rx, especially in your Android application, the question could be, why go for flows? I mean, I'm already happy with Rx. The point is that there are so many things that you give for granted. There are so many things that the coroutine machinery will take care for you when you use the flow, and things are much more easier, especially because flows has been designed with Kotlin. So a lot of things are kind of different, and most of the hardest things like back pressure are handled automatically. So you don't have to take care about it. So I'd like to show you a quick demo about how to implement some operators for coroutines flow. Now, for the people who already used a little bit of flows, you might have noticed that there are not so many operators in the standard library, and that's by design. It is by design because that allows building an operator with flows is actually much easier than compared to Rx. And I want to show you now with a live coding session how we can implement 3 operators and then see their comparison in Rx and the huge differences of lines of code needed to actually do the stuff. All right, let's go with the first operator. Let's go first, just in theory, what does it do? This one is partition. And this partition operator starts with an upstream, let's call it flow, an upstream flow, and takes also a function, right? And this function returns a Boolean, and this is taken from RxJS, as you might notice from the triple equals, and returns you either the partition function, either true or false. And based on that, you choose where to send your value that it just came from the upstream to one of the 2 downstream flows. So the one is that from one flow, we're going to create 2 new flows, all right? One with the values that receive true from the filter and one that receive false. So let's go with the live session. All right. Does everybody see until the last line? It's okay? Great. If you don't, just ask me. So, all right. Let's start a little bit with how to create a new operator when you work with flows. So first of all, no objects. This is just a good old extension function on the flow. And in this case, we just use a generics, but if you want to create a flow just for an extension function, just for a specific flow of integers or whatever, you can do it. In this case, we want to use it for a generic. And it takes, of course, an input, a lambda, in this case, a suspend lambda, that given the type is going to return you the Boolean, the filter. And we want to return a pair of flows. How can we use this kind of thing? Before we implement it, let's see just how it works. So we start with a suspended main, because yes, you can do it in Kotlin. And let's create first an upstream. So to create an upstream, we use this fantastic function that is called just flow, and takes an input, a lambda itself, and it's going to return as a flow. And in this flow, actually, as you can see, create a cold flow, which is important. We're going to only work with cold flows today. and it's the equivalent to cold streams, you know, in Rx. And inside this lambda, we have a new context, a flow collector context, where you can emit the values that you want to generate in your flow. So we just repeat 100 times to emit the count, and that's it. Once this lambda is going to finish its execution, the flow is finished. It's terminated, you know. Now, given the flow, we partition it, given the number, if it's even or if it's odd, you know. And we got in return two flows, the even flow and the odd flow. And this is just, for the one who doesn't know, this is destructuring, and allows to separate, given you can do multiple assignments in one instruction. And well, you partition, and then you want to, you know, use those flows. How do you do it? So you take the even flow and you start collecting. All right, this is the equivalent to observe. All right, but there is no subscription, because, just for the sake, this is just a suspend function. Since we are in a suspend context, we just stop here for the moment. We don't go on with the computation. So this line is not gonna go further here. And we stop here and we collect our elements. So we print just I am even, and I print the element. And I do the same for odd flow. But as you might see here, we have lunge and coroutine scope. That's because since this guy here, it's suspending, for example, if I write here println, okay, ciao. This line won't be executed until the odd flow will terminate its execution. So if I want to even flow and the odd flow to collect concurrently, I have to create a new coroutine. And coroutines cannot just be created just from, you know, wherever. You need to have a parent. And the parent is the coroutine scope. So I create a coroutine scope. And inside here, I can launch, as you can see, this is an extension function of coroutine scope, a new coroutine in which I collect the element. And then in the current coroutine, I collect also this guy here. Now, I could run it, but you know, someone has to implement it. So let's start. All right, so we need to return a pair of flows. And let's see. Flow 1, of course, we use a flow here. All right, and what do we want to do here? We want to collect the upstream. So in the moment someone is gonna subscribe for this guy, we want to collect we want to start collecting the upstream. All right, so we can do this at partition, because look a moment here, we have two contexts here. One is the flow collector itself, and the other one is the flow that on which we are invoking partition. So we can do this at partition dot collect. All right, and we start collecting, and we can do here value. It's just calling it, you know, just better. And then if, you know, we're gonna test the value against the filter. So if the filter is gonna return as true, habits. If the filter is going to return true, of course, we emit the value. Otherwise, we just, I don't know, discard it. The garbage collector is going to take care of it. And then we will do the same, but this time, if it does not pass the filter. All right? And as you might have noticed, this emit comes from this context here. And it just so happens that the Kotlin compiler is smart enough to understand that collect is not from the flow collector. It's from this guy here. So you don't need to write explicitly this from some other guy. It's just, you know, for be a little more clear. And then what do we do here? We return flow 1 to flow 2. And that's it. Now, this is just a very convenient infix function that allows you to create a pair instead of using just a constructor. You could just do replace infix with ordinary call, but it's ugly, so no. And we're gonna use this one, you know? And that's it. We got it. We can run this guy here. And as you can see, unless I did something wrong, you can see that they are collected concurrently and given on the scheduler liking, maybe sometimes hot, sometimes even, and whatever, until more or less 90. Yeah, I am even. Is it correct? Yeah, it's correct. Great. We've done this. Now, it just so happens that in RX Java, there is no equivalent and for this, so I can show you the code for this because there is not, but there is on RxJS. Good luck finding it and understanding it because, you know, JS. Let's go next. Let's go next to another operator. This time, we're going to step up a little bit. We're going to use something more concurrent in our implementation. This is take until. All right. And take until we have an upstream of elements, and we'd like to just mirror those elements to the downstream until some events happens. In this case, another flow as of whatever value and tells us stop. You know, at the first element at this other flow says us to stop, we just stop. All right. And we're gonna spice up things a little bit, and we're gonna do also for time. So I don't know, after 7 seconds, just stop emitting. You know, close the stream. So let's go. All right, now it's alive. Take until. All right. So before seeing actually the main for testing it, let's go straight up to the implementation. All right, let's start with the flow one. In the flow one, this time we're gonna use something a little more. Oh, zoom. Okay, sorry. Immediately. Better? Nice. This time, instead of using the usual flow one, we won't, because when you use emit, you know, of nothing, for example, which is going to be an error, of course, but I just want to show you the documentation. This guy here is not thread safe, and to be precise, if you don't emit from the same coroutine that this guy has generated for you, it's going to really complain at runtime, even if you did not break anything. So better use something that is thread safe. And for this, we're going to use another function. It's called channel flow. All right, and this channel flow does not have emit; it has send. Because this guy here exposes a different scope. This is called a producer scope. And this producer scope is actually both a coroutine scope, so we can create children, and a send channel. Now, what's a channel? A channel is just, let's call it a pipe, some kind of pipe where, you know, someone puts stuff in and someone else just reads from it. And it's thread safe. And both send and receive, they are suspend functions, so you don't really have to deal with concurrency and because the coroutine machinery is going to take care for you. It's going to take care of that for you. So we're going to see a little bit more details on channels at the next operator. For now, I think this is more than enough. What is wrong? It's not really working. Yes, thank you. Comment up though. Yeah, I don't know. And keyboard master advices there. Thank you. And so take until, right. What we're gonna do now, should I go back here? Should I don't know, I might block again. Let's try. So the point is that if you look at this picture now, you're going to realize that we need to do two jobs. One is passing by the elements, and the other one is to look for the first one that arrives somewhere else. It worked. So we're going to do first the first one, which is just launch, because this is a coroutine scope. And inside of here, we collect the upstream. All right. And we just send it. We don't need to do any transformation or filtering. We just send it, you know, until, I don't know, possibly not forever, but until the next flow arrives. Now, we want to check the first element that arrives from the flow. So we use flow.first, you know, this time flow is this guy here, while collect is called on the receiver. Note that. Now this is a suspend function, which means that we're going to stop here until we receive the first element. And to be precise, the first element is going to be returned to us. But are we really interested in the element here? Not really. So, garbage collector on you. And now would like to close this guy here, but how? Well, just turns out that, we get returned something from the launch, and we just cancel the job. And that's it. It's actually done. For the time one, it's actually very similar to the implementation. But of course, we don't have flow. So we should kind of sleep, until I could use thread.sleep. Just don't use thread.sleep in coroutines, like never. There is another one, this delay, which is the equivalent, but for coroutines, for the given duration. Now, some of you might wonder, what's the duration? It's just Kotlin's take on amount of time, all right? It's just an amount of time. It could be seconds, 2 years, 4 years. You don't care. It's a duration. You delay. That's it. It's done. We implemented it. Let's use it. So we have a main here, another one. We have the upstream, which is just a flow of strings where you emit hello, then you wait 1 second. Yeah, that's an extension value for integers. It's very neatly returns a duration. Emit, you return word, and then delay another 2 seconds, and you send nope. And our objective is to not emit nope. And so let's remove this one for a moment. Let's just use the take until. So we take the flow, and we take until 1.5 seconds, and we print, and then we collect it, and we print what we get. And then we do the same for the stopping flow. But this time, the stopping flow is just delay 1.5 seconds, and then you send unit. It could have been whatever. It could have been, stop. We just don't really care because, it's a flow of whatever. And so we can run it. Hello, word. Hello, word. Yeah, nice. No nopes. Great. Let's see the implementation RX. All right. In this file, I have a lot of example with RX with the same things done. So let's quickly fly over this stuff. You can actually see it on the GitHub project that it's published. It's called Lamba92/go with the flow with dashes instead of spaces. It's going to be written at the end of the presentation as well. Let's go with take until, all right, with the observable one. So we reach a nice and great 14,000 line class. Very easy to maintain. And then we actually move to the proper implementation of the operator, and this time we're gonna have a nice 110 something line, 120 something line. I think it's doable. It's still doable. I mean, it's fine, but it's not so easy. Let's go to the next one. Shanwei, this time it's going to be a little more strong, this one. This operator is, let's hope I can go back later. This operator is actually a little more complex because instead of returning new values, it's going to return you new flows, a lot of them. To be precise, it's called groupBy, and you pass a function that, given the value of the upstream, it returns you a new value, a new key. So what you want to do is that you group elements of the upstream by a key that is generated by the value coming upstream itself. And for each key, you create a new flow, a new downstream flow that only has the values for that key. All right, it's more difficult to say than to implement it. Trust me. And let's see it a little bit. It worked. All right. So what do we want to create this time? We want a function that returns, we want an operator, so an extension function of a flow of type v values, and it gets a key selector, a function that, given the value, returns us the key of that value, and it returns us this neatly created data class, which is just the key, and the flow that contains all the values that maps to that key. All right? And what you do with that flow, I don't know, it's on you. In our example, we're just gonna collect right away stuff. But feel free to do whatever. Let's see first the example, how to use it. So we create a range of numbers, 0 until 99, 0 included, 99 and 99 as well. And then we transform into flow. This is standard library function. Almost all iterables can be transformed into flows with this function. And we group it by the last number, the units of the number. So let's say that I have 1004, so the key would be 4. 345, 5 would be the key, all right? This is just the reminder. So, if we divide it by 10, the reminder is always the unit of the original number. And then we receive this group by item, which the structure, to get the key and the flow. And then, since we are in a coroutine scope, all right, we can immediately start collecting the data flow somewhere else in a new coroutine, which is flow, collect, and we print it. We have the key from the original, from the groupBy result, and then the number from the collection of the downstream flow that we just generated. Well, not yet, but let's see. All right. So our idea is that every time we receive a key, every time we receive a value of a specific key, we're sort of gonna have, like, on our hands this flow where we put stuff based on the key. All right. So we need to save that somewhere. I think a map is quite nice in this case. So as usual, we create a map, a mutable map for just for the record, and of course the key is going to be the key. But what do we put in the value? Now, we could be tempted to say, oh, let's put a flow, it's just a flow, right? Well, not really, because a flow you can observe a flow, but you cannot put new stuff in a flow, right? You need some kind of other primitive. And here, channels come very handy, a channel from coroutines, all right? So we have, let's close this guy. We have a channel here, because a channel can both send and receive. All right, we're gonna see in a moment how to receive in this case. All right, but for now it's just channel. We put stuff. Someone is gonna receive magically. And what do we do here? Well, we start collecting. We start collecting the upstream. Do we? No. Sorry. We return actually the new flow that we will create, and inside this flow we actually collect. Yeah. All right, and we have the value here. All right. Now, first thing first, we need to evaluate the key. So val key equals key selector of value. All right, and we have the key. Second, we want to check if the key is in the map, because we want to know if it's the first time we encounter this key or not. So val is key in map with the capital M. In this case, that would be key in map. Magically. And now we need the channel. We need to retrieve this magical channel. We take the channel and we either create one and put it in the map and use it, or we just get it because it was already there. We could use this. We could leverage the knowledge of this guy here, but not really. There is an handy function in the Kotlin standard library, which is map.get or put the key. And what do we put in case there is no key? Well, a channel, and the Kotlin compiler will do the rest, inferring the types. All right? Now, we have the channel, we have the value, we have the key. Let's just send stuff into the channel, right? So we take the channel and we send, for sure, the value, because that is the channel for that key. But who's going to consume the channel? Well, we need to send it downstream, all right? If the key is new, so we never encounter it in the map before get a pull, because of course if you do it afterward there is always if the key is new, we need to, push downstream the new channel, So we emit, because we are inside the flow collector scope. And we should emit a groupBy item, all right? And we send for sure the key. And what do we send here? We can say the channel, right? But, it's not a flow. So the compiler, of course, is going to say, what are you doing? Well, just so happens that you can consume it as a channel, as a flow, sorry. And the channel is magically transformed into a flow. Nice. Now, if we step back, we have to remember that collect is a suspend function. And this guy here is not going to go on. So if I write here println, until the upstream flow is closed, no one is going to execute println. All right? And that's great. We need that behavior because after the collection is finished, it means that the upstream flow has closed. And if you look closely to this image, when the upstream closes, also the downstream closes. Everything closes, not only myself. It worked. And how do we do that? Well, we take the map, we take the channels of the map, and for each channel, we take it, and we close it. And this is going to translate in the receive as flow into closing the flow. And so everybody's happy. Now, before we run this thing, I can spoil you, well, it's broken. It's not going to work. And there is some stuff that we need to take care on actively this time, and it is back pressure, all right? We are not just creating a flow. We are creating a set of flow, and someone needs to consume it, because it just so happens that when we send, look at here, this send is suspending. Oh, let's suspend, like, until when? Why? When this guy is going to be executed? Well, the documentation says, yes, I read the documentation. I know, it's crazy, right? And suspending the caller while the buffer of this channel is 4 does not exist. Buffer. Let's see what this buffer is. All right, so the buffer, a channel, has of course a receive and a send function. But when you suspend to send and when you suspend to receive depends on the state of the buffer. The buffer can be configured for rendezvous, so you cannot send, you will suspend to send until there is someone to receive. Of course, if you receive and there is nothing inside, you suspend because there is nothing to receive. And then, of course, there is a buffer capacity of whatever number, even unlimited. And also there is conflated, which means that there is always space, but you just throw the previous value if it hasn't been received yet. In our case, in our case here, the default behavior is rendezvous. So if you are sending, we need someone to receive it while sending. And who's going to receive it if we didn't pass the flow, the receive channel to anybody? This is going to stay here forever. So what we do here is channel dot unlimited. Because, just put stuff in RAM and, let's wait until out of memory arrives upon us. Or, command shift. Let's see if I remember from SepTalk. Was it property? No. P? Value? No, P. No. Parameter? I don't know. I'll just do it manual, okay? Ooh. No, it's property. Okay, I use this one. Property. And what's this one? Okay, you can see. No. Yeah, okay. Manually it is. Okay. We're going to call this guy buffer. No, like downstreams buffer capacity. That's a mouthful. Of type int that equals by default. Did I write it downstreams? No, not really. Streams. What's wrong with me? Yeah, help me. Thank you, IntelliJ. All right, and instead of here, we let the invoker of this function to decide how to handle the back pressure. And downstream. And of course, we tell the guy that require require downstream buffer capacity not to be channel dot rendezvous, otherwise it's gonna block, you know? It's not gonna work, you know? That's on you. Nice. Okay, if I run this, it's gonna work, but if there is an error inside of here because the user has written some obnoxious code, we're gonna be in trouble because the downstream are not gonna close. Let's see a moment why, because like by unveiling some of the mysteries of coroutine cancellation. Coroutine cancellation means that you have been asked to stop. You know, your coroutine, your thread, lightweight thread, your job has been asked to be cancelled. Maybe because yourself actually had an error, or maybe some of your parents or your siblings, depends on the coroutine scope rules. But you need to stop. And where do you stop? Well, at the next available suspension point. All right, here there's going to be an error either here or here. In this case, if the error is inside key selector is going to throw. You know, and if we throw, we're going to stop immediately executing this guy, you know, and also collect is going to throw. But if collect is going to throw, who's going to close our downstreams? Well, of course, a try catch, you know. And but instead of catching the arrow, we just finally do something, you know. And in this case, we have saved the day. Even if our user is gonna utterly fail by writing the key selector, we're gonna still close the downstream values that it has created until now. Done. Let's run it just to recollect. We're gonna just create a flow for each number for each unit. So we expect from 099 we expect 10 groups, and each of them is gonna print just it, and let's go. It's broken. RSL reference JVM. Yeah, I guess so. Why? Are you there? Yeah, works. All right, as you can see, for example, for number 5, for example, key 5, we have, as you can see, 10 results. 5, 15, but 25, for whatever reason, it decided to do them one after the other. Well, God bless the scheduler. 45 and go until 95. There we go. Now, yeah, we still have a little time. How much time? Great. Let's see RX. All right. This is how you use it. Actually, we're gonna see a little bit the how you can consume RX in coroutine styles, and how you can create RX observables in coroutine style. But for the sake of the moment, let's say that we have a range of numbers that this is an observable, and we use the official function groupBy from RX Java, and we do the same. All right, we got return this whatever, which we don't really know. It just so happens that it's an observable, but it also has a key. And so the key is here. Maybe there is, maybe there is not. Who knows? And here we collected. This is an observable. Just look for a moment. This is a grouped observable, whatever that is, but it's just an observable. All right, and we can collect it just like we do with flows, because in a library that we're going to show in a moment if we have time. From the coroutines team, there are all those needs extension functions to consume them just like flows. And we do the same. We print the key and the integer. All right, let's go. On line 9777, we have this groupBy, which is past stuff. And then line 9900, we go on until it's over 9000. Then we finally arrive to the actual observable groupBy, and this guy here, oh maron, it's yeah, it's good luck maintaining this guy here, it's going to be not easy for the team. But how many lines, just to wrap up here, we used? 31 until 53. Yeah, I don't know maths. How much is it? 27. 20 something. 20 something. Everybody specifically. Yeah, you can see that a lot of the stuff is taken care for you. For example, in observables, you need to think about the schedule, where to put it. This is inherited by the coroutine scope. And back pressure, it's quite easy unless you're really doing something complicated, like in this case. Yeah. Now, can I have an estimate of the minutes? To 5 minutes. 5 minuti solo 5 vedrai. Allora. RX range. Okay, let's see how we create. Okay, so first of all, the packages. We have the Kotlin coroutines RX. Okay, the core is all the stuff that we use until now to implement the new operators. For interoperability with RX Java, there is RX2 and RX3. And there are all those functions to do that. And also there is reactive for the masochists that use the flows from the JDK. There is also that, and it works just like coroutines, you know, and they're only available. Of course, they all share the same release. Please don't change versions, you know, keep the version, you know, the same. Let's see some stuff that we have available. As we see flow and channel flow, we also have RX observable. This guy here is just a channel flow that then converts the resulting flow into an observable, all right, of integers. Also respects the nullability, unlike Java. How to use, for example, the filter here, we can just do the same. Let's see, this is just to create a column observable true. And that's, I'm showing you how to use actually the same function, but this time in the coroutines flavor, you know. Given the range, we do the same take until operator for 800 milliseconds, and then we collect and print it just like we did with the flows, instead of observable, callback, blah 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 blah, and then subscription, and then you forgot the subscription, and then it leaks, and so on. Yeah, that's pretty much the same. Did I forgot anything? No, I think I'm done. So, thank you everybody for joining me. You can find